Okay, so let's look at, as the last point, let's look at a special case. We saw that the principle of work and energy was W dot equals T dot. The rate of change of kinetic energy of a system is the power of all forces acting on the system. All forces, internal and external. Now let's look at a capital a special case. So this is the case where we can let's see, where we can define F. F is the total force, or how can I write this? So I guess total force on a particle for now. Particle. Can write F as minus gradient of a potential function that is only a function of position. So if you remember, gradient is partial v partial x I minus partial v partial y j minus partial v partial z k. So this is the definition of gradient. I wanted to say something else here. So this v, which is function of position, this is important, it has to be only function of position, is called a potential function. Potential function. And it is a scalar. So v is not a vector, v is scalar. For instance, you can think of in XYZ plane, kind of like a ball. This could be your v. Oh no, this is in XY, not in XYZ, XY in 2D, and that would be your v of r. So for any point, you have a certain value for that v function. In 3D, you cannot visualize it like that, but that's easy to visualize in 2D. And another thing, what this means is, so gradient is the direction of kind of tangent to the surface, and it gives us a vector. So this is f at this point, a vector that is tangent to my velocity, to this potential surface, and it's in the direction of maximum change. So that's what potential is, gradient is, and its relation to potential function. So now with that definition, also remember definition of work, dW is F dot dr. And let's work with the Cartesian coordinates. So F is Fx I plus Fy j plus Fz k dot x or dxi plus dy j plus dzk. And we just defined, let's look at the condition that this f is a gradient of a potential function. So let me write it down. Let me take out one minus, equals minus di v over di x I plus partial v partial y j partial v partial z k dot dxi plus dyj plus dzk, and this dot product is partial v partial x dot dx partial x dx plus partial v partial y dy plus partial v partial z dz, which now this is the full dv. Oh, there is a minus. There is a minus here. This is minus dv. So dw, in other words, dw, the infinitesimal work, is the infinitesimal change in potential function, or let me not do this yet, or dw plus dv equals 0, or w plus v equals some constant. Let's call it e. So this is the conservation of energy principle. So remember where we came from the special case. I cannot do this. You get the point. From the special case that we could define f as the gradient of a potential function. So this sounds a little abstract, but you can relate. Well, it is called potential function because it is related. It is potential energy. So as long as you can define a force in such a way, your system is the energy of your system is conserved. And it is important, maybe put here, that all forces that do work should be written as all of them should be able, you should be able to write them as a gradient of a potential function. So in that case, the energy of the system remains conserved. Well, mechanical energy. So let's look at a few examples. Gravity, a uniform gravity version, uniform, the one that we are usually familiar with. In that case, Vg, that is only a function of position, is actually going to be mgy, only depends on the height, not even x and the x position. Mgy, let's call this y, or mgz in 3D. Let's do mgz. Mgz. So in this case, if I take the gradient force of gravity, now you'll see the familiar one, that it's the gradient of v negative, which is minus mg in k direction. So you see, I can write force of gravity using a potential function. Similarly, gravity, but in an inverse squared version, I can write the potential function as a function of position to be minus, let's see, minus k m over some distance from the center of that gravity and center of the mass. So in doing that, the force of gravity is going to be minus k over r squared m in a radial direction. And this is in Newton's equation. It's going to be k, what is it? Mass of Earth, mass of object. No, this is g over k. G over r squared. And the last familiar one I have here is elastic or linear spring. Linear spring. And I can write the potential function of position, to be 1/2 k r squared. Again, r the distance from the center, so the polar or cylindrical frame. And from here, f of this elastic element is minus k r in the direction toward that center. Okay, so what we see here is that the conservation of energy, we saw a more general case of it other than just gravity or spring. As long as we can define our forces using gradient of a potential function, that force is conservative and the energy of the system remains constant. Okay, so it was a very lengthy module. I hope I didn't annoy you too much, and in the next module we will get more into new stuff, the ideas of constraints, how we can handle those, and how we can solve systems when there are more than one thing. Okay, so until then, happy studying.